Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Our first speaker is Dr. Peter Lee. He's the corporate vice president and he oversees operations for encompassing about 1,150 PhDs that we have worldwide as part of Microsoft Research, and that covers 13 labs across the world. Under Peter's leadership, we do the fundamental and applied research in computer science and related areas. And Peter has been in various organizations before he joined Microsoft Research in 2010. He was part of the Carnegie Mellon University and was with DARPA, which is Defense Advanced Research Projects Agency, which is a very well-known agency in the US. And he got his PhD from University of Michigan. And he is on various committees, which includes President's PCAST, which is President's Council of Advisors on Science and Technology, and he's member of Advisory Council of Computing and Information Science and Engineering. And I welcome Dr. Lee to come and deliver the address.
Thank you, Vidya, and thank you, Anandan. It's really thrilling to be here and a great honor to speak to you today. I thought I would try to be a little bit personal and give a personal set of stories about research. And one of the reasons is that today you will really be treated to a whole program of some wonderful lectures by some world-class researchers on a variety of subjects. And as you listen to those things, some of the topics will sound very inspiring, some will sound mysterious and maybe strange, some will sound very interesting to you. But since we're here to try to explain to you why a career in research might be interesting, I thought I would start off the day today just to talk about what is research and why is it important, and what makes people like us want to do research. And it's actually a very interesting question. It's a difficult question to answer. In fact, I find that even researchers themselves sometimes don't fully understand or aren't able to articulate clearly what it is that they do. In fact, one of the most famous researchers in history, Albert Einstein, is quite famous for saying, well, if we knew what it was we were doing, it wouldn't be called research, would it? And that's just a statement of admission that part of the process of doing research is involved in discovery. And when you're trying to discover something new, sometimes you don't exactly know what direction you're heading. You don't precisely define what problems you're looking at. You're just seeking somehow new knowledge, just constantly trying to advance a little bit every day how much people around you and how much you yourself know. But that process is rather mysterious. And so let me try to explain a little bit about what it feels like. And I thought to start, as a first example, I would just describe one interesting computer science research problem, which is known as the pancake flipping problem. So how many of you have heard of the pancake flipping problem? Not too many of you. It's actually a problem that used to be taught quite extensively in schools, and it involves the following. Suppose you have a stack of pancakes, as you see here on the screen, and imagine that each pancake has a unique number written on it. So if we have n pancakes, we have the numbers 1 through n written on the pancakes, but the pancakes are all scrambled in some random order. And so now we can have the problem, can we sort the pancakes so that they are perfectly sorted 1, 2, 3, 4, 5, 6, 7, and all the way to n? How do we sort the pancakes? And we are allowed to do only one type of operation, which is to stick a spatula anywhere we want in the stack of pancakes and flip that part of the stack of pancakes over. And so we can do that flipping process as many times as we want in order to rearrange the order of the pancakes so that at the end we have the perfectly sorted stack of pancakes. And so now the pancake flipping problem is posed as follows. For any stack of pancakes of size n, what is the minimum number of flips that would generally be needed to sort a stack of such pancakes? And that is a problem that has really perplexed computer scientists for a very long time. And computer scientists have been researching this problem for a very long time. And it might seem strange to you, why on earth would people work on such a frivolous, and I would say even fun problem? Such a fun and silly problem as flipping and sorting pancakes. Well, in fact, one of the first important research works on this problem was done by our own founder at Microsoft, Bill Gates. And in fact, this is a snapshot of a research paper that he co-published with a very good colleague of ours at Berkeley, Christos Papadimitriou, that actually first posed an analysis of this problem as well as solution to the problem for stacks of pancakes of size 1 through 13. In fact, provided closed-form solutions up to size 13, and then an analysis beyond that. And in fact, while the idea of flipping pancakes appears to be rather fun and frivolous, and it is sort of a fun problem to think about, in fact, it's a fun problem to talk to children about, it turns out also to be highly relevant to a wide variety of resource allocation problems, in this case, in operating systems, in the early Microsoft systems, disk operating system. And so we see here in research that oftentimes we think about solving a practical problem, in this case, solving some type of scheduling problem in an operating system, but we talk about research in more fun terms. And so one thing that's just cool about research is we oftentimes try to have fun with our problems and talk about things not always so seriously, but in this case, in terms of pancake flipping. It's something I really admire about researchers. Now, of course, it's not just fun that inspires researchers to work hard and to study hard, but sometimes beauty. And here, this is, I think, a really beautiful photograph of the part of the Mediterranean Sea. And the Mediterranean Sea has inspired countless numbers of artists. But maybe you might be surprised to learn that the Mediterranean and its absolute beauty have also inspired some of the most important research of all history. And in fact, it was the first sight of the Mediterranean Sea by C.V. Raman that directly inspired Raman to think about the problems of spectroscopy and the diffraction and scattering of light through materials that ultimately led to Raman winning the 1930 Nobel Prize in Physics. And so, as he stated, in fact, in the very first paragraph of his Nobel lecture in 1930, a voyage to Europe in the summer of 1921 gave me the first opportunity of observing the wonderful blue opalescence of the Mediterranean Sea. And this was just so inspirational to him, that beauty. And what we see here is that researchers think not just of fun and frivolity, but also beauty as sources of inspiration. And so sometimes, if you think of researchers as being so stern and always very, very disciplined and always hard at work on problems, that's all true. But researchers are also always looking for some essential beauty in things. And in fact, the best researchers in the world believe that if something is truly beautiful, then that thing is probably also very important to know. And we see this over and over again in research. Now, I want to say something a little bit about my own start in research. And unfortunately, unlike Raman, when I was growing up, I never had the chance to see something as beautiful as the Mediterranean Sea. And in fact, this is a picture of my hometown in Michigan. And now I do have one kind of common characteristic with Raman, which is that Raman's father was a physicist and my father was a physicist also. And my father studied the physics of lattice and crystalline structures. and in particular properties of snow. And for that reason, we all had to live in a city in the United States called Houghton, Michigan, that actually has about 300 inches of snow every year. And that's, of course, a very important thing if you're a researcher studying snow. And so this is pretty much what it looks like right now in my hometown. Well, so I couldn't really look to something like the Mediterranean for beauty, but I was still attracted to the idea of beauty in research. But it's a different kind of beauty, and let me give you an idea of that. And I'm going to assume here that you have a little bit of familiarity with the idea of computer programs. And so if you understand computer programs, then you can see what I've written here as a program, a very simple program that computes, when you execute it on the computer, the factorial function. Now, of course, as I was growing up, I wasn't growing up as a computer scientist. I was growing up with a father who was a physicist, and my mother was a chemist. And so I was thinking of this as just a simple mathematical equation. And if you look at this as a mathematical equation, we see that we have the unknown variable f on both the left and right-hand sides of this equation. And with that unknown variable f, this is simply a statement of a math problem, which is the problem to solve for the unknown f. And a little bit of thought, if you look at this, will convince you that f is simply the factorial function. That if we substitute the factorial function for f in both the left and right-hand sides of this equation, then the equation will hold. And so, as I was first being introduced to ideas in computing, this seemed quite straightforward. There was nothing new in computing. It was all just simple mathematics. Well, later on in my studies in college, I ran into work by other computer scientists, most notably a man named Dana Scott. And Dana started to pose more interesting questions. And one of the questions he posed is, well, here's another equation. And if you look at this equation, it is an equation with an unknown f. And the factorial function solves this equation, just as it solves the first one. And yet, if you look at this second equation as a computer program, it does not give you the factorial function. And as I started to study what computer scientists were doing, it started to dawn on me that mathematics, that ordinary mathematics, was not adequate to describe computational functions or the notion of computing. And for me, as someone who really grew up in a life of physics, of chemistry, of mathematics, the sudden realization that there was something new that couldn't be described with physics or chemistry or mathematics in computer science struck me as an intensely beautiful thing. And so this is, of course, a completely different notion of beauty than the idea of looking at the Mediterranean Sea and its magnificent blue colors, but it's a beauty nonetheless. And for me, this beauty also seemed convincing that somehow understanding why and how these kinds of equations must be something new in computer science, it also convinced me it must be something useful. And in fact, decades later, even in companies like Microsoft, the theories that arise out of trying to understand those kinds of equations lead to very practical tools. And in fact, one tool that almost every Microsoft developer around the world uses has something called a static driver verifier. And a static driver verifier actually uses the principles that come out of the kind of study of these kinds of equations that every day make Microsoft Windows and Microsoft Windows Phone much more reliable and much more secure than they have been in the past. And so it's just, to me, an intensely beautiful thing to see such beautiful theory lead to such practical results. Now, we see researchers trying to have fun. we see researchers really attracted to beauty. But again, that doesn't mean that it's easy for the world to understand why research is valuable and why research is important and why we do research. And in fact, as I finished my PhD studies and I went on to be a professor at Carnegie Mellon University, even though I was hired as a professor at Carnegie Mellon and I was very well respected by my peers, even my manager, my department head, didn't understand why I was attracted to such things. And in fact, I remember one day my department head at the time told me, he asked me, why do you do this kind of research? And I told him, I do this kind of research because I think it's just so beautiful. And of course, then he made me feel not so secure in my job by saying, well, if you think that beauty is important, maybe you should be a professor in the School of Art instead of computer science. Luckily, he moved on to a different job, and I had a later department head who understood the importance of beauty. But the point here is that, again, we see how hard it is sometimes for people to really understand what it is that's important about research. Okay, so moving on from fun and beauty and the challenges of that kind of understanding, what I'd like to do now is to give you a simple test to illustrate yet a third principle about research. Okay? So what I will show you on the next slide is a picture, and the picture will have a bunch of dots of different sizes and colors. And I will show you the picture for just 5 seconds, and what I would like you to do is within that 5 seconds, I will take the picture away, and I want you to tell me how many red dots there are. Okay? Everyone understand? All right, so here we go. Concentrate hard. 5, 4, 3, 2, 1. Okay, so how many blue dots? So, it's a dirty trick. But there's a point. And what is the point here? Look, when we're working on pancake flipping, when we're just consumed with the fascinating beauty of these mathematical equations that aren't easy to explain with ordinary set theory, when we're doing these things, in essence, we're wandering, we're exploring, we're playing. I gave you all a job, and your job was to count the red dots, and I'm sure you're all very good at, as students, you're very disciplined, and when you are told to do a good job, you do a good job, and there's a level of focus and discipline that you all exhibited. In research, there are times when we also exhibit such focus and discipline, but it is just as important in research to, at times, step back and just let your mind wander and just to let your kind of soul be free and to explore new concepts and try to be so-called out-of-the-box thinkers. And this is important, an important role for research in Microsoft and in fact in many places. In Microsoft, we have many product development teams that every day are doing a very disciplined job to build and design new products, to develop them so that they're reliable and that they're a joy to use, to create great advertising so that customers know that they exist and what they do, to sell them in all the best stores. And that discipline is equivalent to counting those red dots. But the thing is, sometimes the world changes, and sometimes we need, as a company, to know something else, something surprising. And this is where research can come in. And so as researchers, when we're exploring pancake flipping, when we're exploring something about the Mediterranean Sea, that is very much like wondering what other kinds of colors are there, and why are there different kinds of colors? And all these other questions that are present in that picture, those are just like all the other questions that are present in the world of computing, in the world of research. And it is a role of researchers to be curious about those things and to look. And every once in a while, as we'll see in some upcoming examples, knowing those things can come to the rescue. Knowing those surprising things can help you be more competitive and to be more successful in the future. And so a third role of research is to have the kind of ability to be an early warning system, to know more about the world, and to have a broader curiosity just in case it's necessary, and just for the goodness of knowing more about our world to push the frontiers of human knowledge. Now, a fourth thing I want to say about research, and that is, of course, we can be involved in research in many different disciplines. As I explained before, I grew up in a household where I had a father as a physicist and a mother as a chemist, but why did I end up in computer science? And there are many reasons for that. But one very important reason is illustrated by the following little parable that I'd like to give you. And this parable goes back to the year 1969, which is arguably one of the most important years in human history in science and technology development. And the reason for that is there were two major events that happened in 1969. The first event being depicted here, which was the first time we put a man on the moon. And so this is a picture of Neil Armstrong in 1969 at the first moon landing. A tremendous scientific and technological achievement. A huge number of problems encountered and overcome. 50,000 people all working together on a single goal to put this man on the moon. And the spin-off effects of all the technologies and all the new knowledge that came out of this have really transformed all of our lives. Now, what is less known is that in that same year, 1969, there was another major technological achievement. And it was much more humble at the time, but in the fullness of history, we can see is every bit as impactful. And that is the birth of the internet. And in fact, in 1969, we had the first demonstration, first of 2 nodes and then of 4 nodes, being connected together across wide distances to connect computers together using the early versions of the Internet Protocol. And then something that happened at the Stanford Research Institute to use that network to give what is commonly referred to in computer science as the mother of all demos. And this was done by Doug Engelbart, who basically used this early 4-node internet, at the time called the ARPANET, in order to show the capability of a person in Utah and a person in California collaborating together on a document. And so what was really just visionary here was the idea, as Doug Engelbart puts it here, that we might be able to use such networks of computers in the future to augment human intellect. And just, again, like the moon landing, an amazing technological and scientific achievement, one that has had just long-lasting impact. Now, what I'd like to do here is just ask a question, and it's a little bit of a silly question, but I ask it for a reason. As you look at these 2 major accomplishments in 1969, well, looking back over the last 40 plus years, which of these 2 events ended up having more impact on our lives? And of course, it's a silly question. In fact, let me admit that I was 9 years old at the time that these things happened, and I was completely fascinated by the moon landing. I watched it on television every day. And in fact, I think I was inspired to be a researcher and a scientist because of that. But one way to answer this question is to ask, how many of you have a sister who's been to the moon? Or a brother? Or any kind of relative? Or if you are a parent, how many of you have a child that's been to the moon? And of course, it's a little bit of a silly question, but the point is that the internet had the effect of being democratized, was a technology and is a technology that can touch almost every person on the planet. And this is in contrast to the moon landing, where the Saturn V booster technology or the lunar landing technology is something that is just so rarefied and so exotic that its broad impact on people is somewhat limited. And so, for me, as I look at the possibilities of computing research, one of the things that's so wonderful about research and computing is that new ideas and new research knowledge in computing have the potential to reach almost every person on the planet. And that potential is just incredibly important and incredibly exciting. And so even the most humble ideas in computing can have such broad impact. And for me, this is something that gets me up every morning. It makes me excited to be involved in the computing field and in computing research. And so let's run through a more complete example. And for this, I'm going to really now focus on examples of research drawn from Microsoft and Microsoft Research. And to set up the problem, I'll use this image from an old Star Trek movie, the Star Trek The Journey Home. And I don't know how many of you love the movies or have seen this old movie. I think this movie was probably made before most of you were born, but it was a favorite of mine some years ago. And the setup of this movie is that the Star Trek crew from the 24th century finds out that the universe inhabited by mankind is in serious danger of being destroyed. And so they have to save it. And in the process of figuring out how to save the universe, they realize that they have to go back in time to today's Earth and fix some events that are transpiring. And only by going back this 400 or 500 years and fixing these events can they avoid the cataclysm of destroying a big part of the universe in the future. And so in this scene that's depicted here, the crew of the Enterprise, Starship Enterprise, goes back to modern-day Earth, and they quickly find a computer, because they need a computer in order to help fix things. And they find a computer, and immediately they want to start using it in order to hopefully save the universe. And in this scene, Scotty, who's the best person to use a computer to save the universe, encounters this machine and doesn't know how to use it. He starts talking to it. Of course, nothing happens. Then he sees the mouse, and he figures, oh, of course, that's how you use it. So he picks up the mouse and starts talking to the mouse. And so it's funny. Now, it's funny, though, because any of us who have ever used a computer have had the frustration of how to interact with a computer, and of course, the frustration of not being able to talk to a machine. And in fact, it is a real problem in computer science research to have machines that we can talk to, that we can converse with. And so I'd like to describe a little bit of the work that we've done at Microsoft on this problem. Now, before I can do that, I have to explain something about a field of computer science called machine learning. Machine learning is a part of computer science research that involves the study of computing machines that get better with experience. And one of the first machine learning problems that people worked on was to try to build a computer that could look at an envelope and understand the address that was written on them. And so if we have an envelope like this, and we look at one of the digits that's handwritten on the envelope, we want a computer to be able to look at that digit and understand that that is the digit 2. Now, that has turned out in the early years of computer science research to be a very difficult problem. In fact, there were many researchers working on this problem and really struggling because of the huge diversity of ways that people write their addresses and digits and the huge number of ways that that people put addresses and things on envelopes. And so, in fact, it turned out to be very, very difficult. And so as people tried to write computer programs to recognize the digit 2, they ended up having to write a huge number of rules. You can imagine a rule that says, well, if you see a little loop in the lower left-hand corner of the digit, it's a 2. But not if there's also an opening on the upper right, then it might be a 6. Oh, and if there's a loop on top, then it might be an 8, and so on. And after a while, you get more and more rules that start to interact with each other in bad ways, and there's certain brittleness. And the systems really don't end up working very well. So an alternative way to solve such problems is to use this concept of machine learning. And you'll hear much more about machine learning from some really world-class machine learning researchers at Microsoft later today. But just to give you a little bit of a primer on this, imagine we want to use machine learning to solve this problem of writing a program that can accurately look at a handwritten digit and tell you what digit it is. That would be called an accurate digit classifier. What we do in machine learning is, instead of writing down all those rules, we instead provide a huge number of training examples. So we gather a large number of handwritten digits, we label the correct answers for all of those training examples, and then we feed all those training examples to a machine learning system. And machine learning system then trains or analyzes all of those training examples, and from that automatically produces the digit classifier without the need to manually think about what all the rules are. And that idea of machine learning now has become so successful that accurate digit classification, in fact, is used routinely by the postal services around the world, as well as on mobile phones to read menus and street signs and so on. And so it's been wildly successful. So coming back to speech recognition and being able to talk to a computer, we can imagine trying to use machine learning to understand what it is that people are saying when they're talking. And in fact, there was quite a bit of research to do this in the computing research world. And so in fact, what you see here on this graph is the progress of machine learning-based speech recognition, the ability of a computer to listen to someone speaking and tell you what words they're saying. And on the y-axis, what you see is the error rate, the number of words that are misrecognized. And as you can see, as you go down, you're getting fewer and fewer mistakes being made over time. And so this has been really another great victory and a great example of the applications of machine learning to a very hard computing problem. Now, of course, one thing about research is that sometimes we get stuck, because researchers will tackle the hardest problems that we can find. And in fact, in speech recognition, as you see along the x-axis, the years go by, we did end up having a period of about 11 years where, as a research world, we made almost no progress in making speech systems get better and better. And this is yet another point I want to say about research, is that researchers are patient, and researchers are persistent. And so even though we, as researchers, didn't seem to be making noticeable practical improvements in a computer's ability to understand what people are saying when they're speaking, we kept working on it and kept working on it and kept increasing our knowledge. And after many years, finally, we were able to have enough knowledge to make new breakthroughs that led to new improvements. And so that persistence and that patience and the long-term view is another hallmark of great research and great researchers. So unlike many parts of the business world where people want quick payoffs, quick answers, quick solutions, researchers want that too, but researchers can also understand that sometimes you have to work maybe for 10 or 20 years in order to have a big payoff, and that persistence can be important. Now, in fact, that dramatic improvement just a few years ago was a result of some great work between the University of Toronto and Microsoft Research, where we developed an idea of using a form of machine learning called deep learning to a speech problem, and we published many papers on this that have become quite important in the field. And that led, about a year and a half ago, to a wonderful demonstration where the founder of Microsoft Research, Rick Rashid, was able to give a speech in China to an audience very much like this. And it's important to note that Rick Rashid does not speak Chinese, and yet we were able to use our computer systems to translate his speech into Chinese as he spoke English, and translate it and then speak it in Chinese in his voice. And so what I'd like to do is just play a few seconds of that demonstration. So watch this. And so maybe we won't see that. But the speech was just an amazing thing where he just spoke and out of the speaker system, just as you're hearing me, came Rick's voice in Chinese. And in fact, I remember sitting in the audience, and as I looked back at the students, some of the students were in tears just at the dream of using a computer to eliminate the language barrier. What a wonderful thing. Since that time, we've taken the results of that kind of speech recognition and applied it to many of our products. And so if you use the Bing search engine, you can search using your voice. And if you have an Xbox, you can also control your games using your voice. And this is all using the same kind of technology. And furthermore, the ability to use machine learning to translate different languages is empowering many businesses to do better. And so, for example, if you are shopping for dresses in Russia on eBay, you get very precise translation of the unique language of women's fashion design through machine learning provided by Microsoft Research. Incidentally, I wanted to get back to the fun aspect. It's not just all inspiring people by eliminating the language barrier. It's not all just helping businesses like eBay, but it's also fun. And in fact, knowing that this all was sparked by the dream of speaking to computers as depicted in the Star Trek movie, we even use our translation systems to allow you to interact and speak in the Klingon language, which was created by Star Trek. And now, looking ahead, we have bigger dreams of enabling tools like Skype to provide rapid translation of what you say. And so imagine if you were to speak in English in Skype to someone in German, but all that your German counterpart hears is German in your voice. And so we're very hard at work on that kind of technology now. And so as you look at this, you see that we move from very blue sky research, where we're really just trying to understand how can people understand speech and how does that translate to a computer, to making a great demonstration that inspires people and is very disruptive, to bringing business value in products like Bing, and then thinking ahead to enhancing our products like Skype. We see a pipeline from basic research to tech innovation. And in our management of Microsoft Research, we put these things into a quadrant system, where on the x-axis we look at short-term to long-term research where we want a short-term quick payoff, to research that requires more patience and a long-term view. And on the y-axis, research that is reactive to everyday practical problems, all the way up to just pure exploration, just to understand something better or the search for beauty. And in our management discipline, then, we look to make sure that in our Microsoft Research labs around the world, we are doing all of these different kinds of research, that we are looking at blue sky research, disruptive research, very mission-focused research, and sustaining research to make our products as best as possible. And by doing this, we hope always to be the smartest people in the industry and in the research world, to always be the first with brand new disruptive ideas, to be responsive to society's needs and to our company's needs, and to make sure that we're the best at what we do. And for all of us at Microsoft Research, we're all motivated as researchers to achieve all four of these kinds of traits and characteristics. And so, to summarize, basic research can be hard to understand. It can be hard to understand why people engage in research and what it is that they do. But as I take a step back and I look at the qualities of basic research, I see that it's fun, it's beautiful, it can be really quite challenging, it's always unpredictable, you never know what you're going to get, and ultimately, particularly in computing research, it has absolute ability to impact everyone in the world. And put all together, I conclude that basic research is just the most important thing that you can devote your life to. And so I hope many of you will think about that and make your own decision to devote your life to research too. So thank you very much.